Well, welcome back, everyone, and welcome to those who have not been there in the first part. For those who are joining us anew, I will still go through a few of the same slides that I did in the first part, but it won't take too long. So I'm Dainius Masiliunas from the Laboratory of Geo-information Science and Remote Sensing at Wageningen University and Research. And here you can also see my supervisors for my PhD, Mendin Erdin Sanbazar, Martin Harold, and Jan Wesselt. And the other people listed here are from the Copernicus Global Land Operations Land Cover project. And in this presentation, I will be focusing on the final parts of the content here. So specifically land cover change detection, how it was implemented using BFAST, and I also will mention a bit about the OpenGeoHub project. So just to give a bit of a summary, we're talking about land cover here. So land cover maps are what we generally can see on the ground. So it's trees, grass, water, urban, or other things like mosses and lichen and other things that we might be able to discern from satellite imagery. And knowing what is on the ground is important because then we can quantify it and we can also track how it changes over time. And land cover is a key variable for several of the United Nations Sustainable Development Goals. And because it is very important both for governments to set policy because they can tell how land cover was in the past and then how it will be in the future. It allows us to monitor the current situation, predicting the future change, and it can also be useful for both landowners on the ground as well as modelers who want to predict, say, the change in climate or the population development. And thanks to Global Satellite Imagery Time Series, we can do it globally as well. And this updating is also very essential for effective monitoring. And this updating part is specifically what I will be talking about in this session. So one of the things that I did for that was in the context of the Copernicus Global Land Services land cover project. And just as a reminder, the project is aimed at producing global land cover maps at 100-meter resolution, and specifically from 2015 updated yearly as an operational service. So far we have the collection 2 released, and in a few days you will be able to also download collection 3. And collection 3 is specifically with yearly updates. So you can follow the release schedule on Twitter. The first one is the main one, VTO Remote Sensing, and also the Copernicus channels. It's very exciting that collection 3 is coming out soon because that will have both the updates for all pixels in the world from 2015 onwards, as well as quality indicators for the pixels as well, both for the input data and for the algorithms themselves, and including some spatial accuracy maps. So what I did specifically for this is something that is not yet in this figure, and that is the updating of land cover maps. And I can go to this part. So yeah, I can mention that when I was working on this, I was working in the Terrascope system, which is a cluster that is provided by VTO. And in the cluster, you get a virtual machine, which has about as much resources as a regular laptop, so 4 cores, 8 GB of memory, 1 TB disk space, and it's also running CentOS 7.4. The nice part about it is that it has direct access to the data. So specifically, I was using level 3 top of canopy composites, which includes radiometry of the 4 bands of the satellite. The satellite's here. And also, it includes access to the ARD, which in our project was developed to mask out the clouds better and to remove temporal outliers and do also data infilling so that it's analysis ready and you can do your time series analysis effectively. And it also has an access to the Apache Spark cluster. So there's a cluster of quite a lot of machines, and you can generally get over 1,000 cores if you write your programs and wrap it with Spark, so it can run on the different workers of the cluster. Yes.
Can I ask you,
Yes.
that time frame,
Mm-hmm.
take 1 month to say, yeah, but that kind of extract take 1 month
Yeah.
without parallelization?
For the extraction, you cannot easily parallelize that because it's on a network attached storage. So even if you try to have 2 threads reading from 2 files, it's still going to be as slow because there's just like 1 head and you don't really know where the data is. So it doesn't really make a difference. Yeah. Yes, so this is the part that I want to cover in this session. So specifically what I was doing is doing line cover change detection to enable the map updating. And the obvious way to update line cover maps would be to just classify maps for every year. And you can expect that that should give good results. Unfortunately, that does not happen because if you reuse the same model for the upcoming years, there are a lot of spurious changes. So that's because the algorithm thinks that, well, this looked like forest. Maybe it was 51% sure that this is forest and 49% sure that this is grassland. And now it is 51% sure that it is grassland and 49% that it is forest. And so the tipping of this makes it so that the predicted best guess of a line cover class is now grassland instead of forest. If we look at the differences between the maps, we would see that there was a line cover change, but actually there's no change. It's just the model thinking that the most likely class is now different. And also, so we can use different things to make it better. We can use the time series, and we can check whether there's any breaks in the time series to see whether a really significant change has happened or not. That way, we can use the change detection methods to constrain the changed pixels to a smaller subset, which we are sure that it has actually changed. Another thing that can be done is to use expert rules to determine which transitions are possible or likely. So for example, here we can see an example of unlikely line cover change. So a change from urban to water is something that you would not expect to happen because that would mean that you have an entire urban area completely flooded with water. And that can happen in some cases, but that's not something that is very oftentimes the case. And in most cases, if a model is showing that something has changed from urban to water, it means that it just made a mistake because both urban and water are quite similar in its special characteristics because there's no vegetation on it. Yes?
There's no way to like set the seed for this random thing that you was having for the
Yeah.
I think yeah, for like a random
Yeah. So for those who are at home, the question was that whether we can set a seed for the models so that for every year they would keep detecting it the same way as it was before. Yes, we can. So we can, instead of training a new model for the new year, we can reuse the same model and just give it the new data from the new year. That's actually the way that we are doing it in the project itself. The problem is that it's not just the randomness of the random forest, but it's also the randomness of the input data. So the input data will have changed slightly, and then it will still go to a different pathway in the random forest, and it will still give you a completely different outcome. So especially because random forest by itself, it uses thresholds. So if you go against that threshold, then you will get a different outcome. So indeed, it doesn't really work that way usually. Yeah, So the export rules are useful as well, and that's actually something that we're using in the project as well. There is something called a Markov hidden model, which is a post-processing approach, so that if we have land cover classes over a longer period of time, we can give likelihoods to specific transitions from one land cover to another. And then if the land cover does not conform to those transitions, then it will get forcibly reset to a configuration that makes more sense. So for example, if we have something that's grassland and then it's immediately trees and then it's grassland and it's trees again, that's very unlikely to really happen because for trees to regrow, you need several years. So then the model would make it so that it's only trees throughout the entire time. And so that's one thing that the project did. And I specifically looked into the time series break detection. And this is what I will cover in this session. My task was to see which break detection algorithm and vegetation index works the best for global land cover change detection. And for doing that, I was using BFAST. So BFAST is a set of algorithms for detecting change in time series, specifically for detecting breaks. It's also the name of one particular algorithm in the BFAST family. And the way that it works is that it takes a time series. So we can see here the time series at the top. And then first it splits the time series into components. So it has a seasonal component. You can see that the seasonality is captured here. It has a trend component, so only trends are captured. And then the remainder. So if we take both seasonality and trend out of it, what remains? And then based on this, it detects breaks in both the seasonality and also in the trends. And it tries to segment the time series based on that. The way that it works is that it does piecewise linear regression. So it tries to see where do you construct these different segments so that it would minimize a particular statistic. In this case, it's determined by BAC. And if we have segments of the same parameters, so the same seasonality, the same trend, and we have these segments that have different coefficients between them, then the boundary between those two segments is going to be the break. So for example, in this case, we see several breaks. We see one here where clearly the trend has changed. We see here, well, the trend even reversed. We see another one here, another one there, and another one there. And yeah, this way we can detect all the breaks in the time series with one caveat, in that we cannot detect breaks at the very end of the time series, at the very beginning of the time series, because we have a parameter h, which determines the minimum segment size. So it doesn't try to detect segments that are smaller than this amount of samples. And I was working specifically on a variant of BFAST called BFAST-ON, which is a working title. We might just call it BFAST Lite later on. It's the same concept, but instead of having this subdivision into the different components, it's just trying to detect breaks in all the components at once. This makes it much faster. It can also handle missing values in this case, because instead of doing the decomposition with STL and R, which is the usual way that we will do it, and STL doesn't actually handle missing values. In BFAST-ON, we are just using a data frame, and it's just emits the values that we don't have, and we calculate all the things that we want. So the seasonality, for example, is accounted for by a harmonic model. So it just calculates the harmonic model using the regression, and a regression doesn't need to have time steps that are regular. So just computes the harmonics, creates a new column with the harmonic coefficients, and then afterwards, this is put into another, the piecewise regression model, and it also doesn't need to have regular time steps, so it can just detect the breaks on the boundaries. Yes, so it can handle missing values. It does everything in one single pass. It can also make use of different types of seasonality adjustment. So for example, we can use no seasonality adjustment. So then our modeled time series, in this case, would be just a straight line going up or going down. It can use the harmonics, like in this case it is. So the model is showing the seasonality and it's trying to fit the data based on the seasonality. It can also use seasonal dummies, which is another way of looking at seasonality. Specifically, that is data-driven. So it's just segments each year into a number of segments. And then it just takes the average over all the years that we have. And then this is considered to be the seasonal dummy. So every time that we have that particular time of the season, the model will just take a jump up or down, depending on whether that intercept is higher or lower. So then it can model things that are more complex than what a harmonic model can model, because it doesn't depend on any pre-existing shape. And yes, so because of this, it's also an order of magnitude faster than BFAST itself. And that's in addition to the extra speed improvements that were done by Mario Sattel. He was working on optimizing the BFAST package and moving the critical code paths to C++. So this is much, much faster than what you would get with the default BFAST. So this is the general idea, how you can visualize it. You have the actual data, you have a model that is fit on the data, and then after there's a break, you have a new model that is fit to the data. And if those two models are significantly different, according to BAC, it will determine that there should be a break, so we should have the new coefficients in these two different segments. And then the difference between the two is the break magnitude. So the coefficients change a lot. That probably means that the magnitude is also high, because then the line cover is quite different between previous and later. Yes?
And it also detect gradient changes. So without the break in specific point, but just degradation of force down to the people.
Yes. So the question was whether it can detect gradual changes, and in a way it can. The way that it would detect gradual changes is that you have a regrowth that's going up, and then it will detect a break before the regrowth happens and after the regrowth is finished. So then you have a trend like this, and then you have a trend like that, and then you have a trend like this. Yeah. And then, so BFAST-ON was one algorithm that I used, and then as I mentioned, it has the limitation that it cannot detect the breaks at the end of the time series. But that is something that we also needed in the project, because we want to classify all the line cover until the current day, so until the end of 2019. And BFAST monitor is made specifically to detect changes at the end of a time series. So you have to manually specify which is the history period from which the model learns about what is the normal state. So what's the usual seasonality of it, of the pixel, and then the monitoring period, which it checks whether it still conforms to the same seasonality and other parameters that we had from the previous histories part. So yeah, this is used specifically to create this NRT map, which is the map of 2019. Since not yet a whole year of data is available, since we're not at the end of 2020, and that means that we cannot find breaks using BFAST-ON for 2019. So we need to use BFAST monitor. Yes, so as I mentioned, I used Terrascope to run this, and it's a Spark cluster, and at the time when I was running it, it gave me around 1,200 cores, which is quite nice to have. I split each of the Moses tile into around 2,000 chunks, and it was very useful to use GDAL build VRT because I didn't need to physically do that. the nice thing about it is that it doesn't just mosaic, it can also give you smaller chunks of data. And then I could create these 2,000 chunks that didn't really have any data. They only had pointers to the original data. That saves both time for processing as well as a lot of disk space. And then BFAST itself is implemented in R. So I use Spark R to send the R scripts to the driver first, and then the driver sends it to the executors, and then everything is running. I also get logging, both done by Spark. So Spark has an internal log, and any errors or any messages get logged into the buffer there, as well as into a flat file, so that if the log fails, because, for example, there's some problem with R itself, I could still have some information about at which step did it fail. And then after some back and forth, fixing some bugs and peculiarities that Spark had, I managed to get it running quite well in an automated fashion, so it can handle each tile of POV imagery, detect the breaks in the time series, and output layers where for each year, I would have an indication whether there was a break detected during that year. If there's no break detected, then it says -99 means no break. If there was a break detected, then it gives you a particular time of the year during which it was detected. And then after, if we have, say, no data, if there's too many clouds, so you cannot really tell, then it gives an A. And then in the end, all these small chunks get mosaiced back into a tile locally, once again using GeoBuild-VRT, and we get a global mosaic out of that. So it's running in R. I was running that manually just through Spark R, but in production, we integrated the R scripts into Python using RPy2. That's because in their processing chain, they had it so that the data cubes that are the input for BFAST, they are made in Python, they have all the metadata there and so on. So it's more efficient to just directly map that data cube, move it to R, and then get R to upload the layer, and then move it back to Python, and then have Python write it back, rather than to go through the intermediary step of outputting a file somewhere so that R can read it again, and so on and so forth. Yes?
Is the implementation of BFAST we have done on model statement?
Yes.
Times the 8 days composite, or which one?
Yes. So the data that we were using for BFAST was MODIS data that was at, I believe the composting was 10 days. And it's actually a time series that starts in 2009. That's because on the cluster, they had that data already because, well, they had other users for the same data. So it was fairly simple to obtain it. And it was already pre-composted, already with clouds cleared out and so on. So it's already analysis ready, so it was easy to run it. And the reason why we're using MODIS is that it has this archive going back to at least 2009 in our case. ProBV itself only starts at 2014, so you can see that we would lose half of the time series data if we started with that.
And did you apply BFAST to a vegetation index or to the single spectral signature?
Yes, we applied BFAST to the vegetation indices, and there were several vegetation indices that we tested, and we checked which one performed the best. And to know how well they performed, we needed to have something to benchmark against. So I mentioned that we have the data sets that was created by EASA for training the random forest model in the first place. Now they also collected reference data for change. So specifically, the world was stratified using different land cover maps that are not ours into areas which might potentially have some change. And then something from there, the experts detected whether there was a real change or whether there was no change. In most of the cases, we in fact saw, even after certification, that there was no real change. At the very beginning, it was even quite odd how much there was no change, because we had like 1,000 points that we collected, and the amount of change was 60 points out of that. And we had to do some extra cleaning outs, especially to remove all the instances of fire, because fire is a complicated thing that it doesn't really change the land cover. It was grassland, it was on fire, and then it was grassland still. But it has a very big effect on the time series itself. And yeah, so this data set was collected. Later on, we got more change points that we can use to benchmark it. And in the end, I used this to optimize the parameters also of BFAST and BFAST monitor, as well as to select the vegetation index that would be the best for this.
Sorry, the parameter, which are the parameters?
Yeah, I will explain this, I believe. Oh, I actually have it here.
Yeah, you can explain it.
Well, but this is a good opportunity to do that. Yeah. So the parameters are, yeah, for one thing, the main parameter that we have in BFAST is the H parameter. I mentioned that is the minimum segment size. And that's one parameter that we did not optimize because we have it preset to 1 year, because we cannot have anything that is shorter than 1 year, because then we would have multiple breaks during the year, and that's not what we care about. We also cannot have it longer, because then we would need to wait even longer since 2019 to be able to detect breaks. So we had no other choice but to just preset it to 1 year. But we have other things. So we have this formula here. So in this case, the formula says response is our time series. And then this is what is modeled by. So if we say only trend, for example, then it will make a straight line, and it will not model any of the harmonics or seasonality. If we say trend plus harmon, it will also include the harmonic model. And we also have different orders of the harmonic model. And we also have this ability to use seasonal dummies instead of the harmonic model. And then we also have, in addition, for BFAST ON specifically, yes, here. Since it's doing piecewise linear regression, and then it determines where the segment borders should be optimally, it uses the information criterion. So as I mentioned, the default is BAC. If you recall, BAC is with a penalty of log n, and n is the number of observations that we have. AAC is less, so it's much weaker than BAC, which means that for BAC, it will detect fewer breaks because it will try to not create too many segments with different coefficients. But even BAC was too lenient. So we saw that there were still too many breaks that are detected in the time series, which means that we needed to go with something even stronger. And then what I did is I implemented LWZ, which is stronger than BAC for n that is high enough. And it definitely does better in the sense that it only detects breaks when it's clear that there is a break. So you can see example here. So the black line here shows the breaks that were detected using BAC, and the teal line shows breaks with LWZ. So you can see that generally, in some cases, they just agree completely. But in some cases where, it's not clear whether this segment is actually a real change, BAC will still say that it is, and it will create a segment like this. LWZ will rather just look at these general trends that this is a change that is going downwards, and this is a change where it's not going downwards. And this is the comparison of the residual sum of squares and BAC and LWZ. So usually RSS is just going downwards the more segments we have. And BAC eventually stops. So in this case, it stopped at 4. but LWC is stronger, so it stopped already at 3, and it's not even that much different from just stopping at 1, which means that it would only have 1 break somewhere here, probably. So yeah.
Use LWC.
Yes, so this is also one thing that we needed to optimize to see which one is the best. It's also not always clear-cut whether this is better or not, because it also depends on what is our objective. Yeah, and here you can also see how we can decompose the time series into a trend component and the seasonal dummies, and also into the harmonic components. I will also explain that a bit more in detail later. Yes. And yeah, I can also mention here that for the vegetation indices, we were looking at several of them. So in DVI, EVI, NIRV, and DMI. And I found out that there's not really that big of a difference between them as far as BFAST is concerned. And then we ended up using NIRV partially because it was a bit more sensitive, so it doesn't have this issue of oversaturation like in DVI does. And another thing is that it's not using the SWIR band, and the SWIR band is of even lower resolution in MODIS data. And we're already at quite a low resolution because we are using 250 meter pixels, and our mapping unit itself is at 100 meters. So we're already going to miss some of the changes that we have. Yes. And yeah, just to mention that what we're looking at here is time series of a vegetation index. We're not looking at land cover. So we cannot really determine what changed to what just from BFAST. We just know that there was some sort of a break in time series. So in any case, we need to pair the output of BFAST with some classifier that would be able to identify what this is and what that is. Ideally, the classifier would also make use of this information and then look for the classification only in this area that is stable and also in this area where it's stable again. Yes, and so in the future, we will need to scale it down even more so. So we're moving to 20 meter resolution pixels from Sentinel-2, which means that we're looking at scaling from MODIS 250 meter pixels to Landsat at 30 meter pixels. So that's a lot of more data. And already BFAST is actually a very data intensive and time intensive algorithm because it needs to iteratively try all kinds of different combinations of where to put the breakpoints to get the optimal one. Which means that we have a lot of big data computation issues. Even after these 2 optimization rounds, it's still not running that fast.
But that one can be faster written in C++ and then brought about in R, or is it would that be written in R?
So BFAST itself is written in R originally, and then Mario Sattel, he optimized it and replaced some of the core components with ones running in C++. And then we also have another version of it that is running on Python, which has an implementation where as a backend, it can also use GPUs. And that is generally much faster again.
So do you think the bottleneck is due to the implementations that would really have to fact that you have to implement C++ and pull out the E4?
Yes, in part to this. Definitely, if we move to GPUs, it is much faster because these are all very independent things. So for every pixel, we have a completely different thing, and then it's much faster if we do it like that. So indeed. So it's a matter of data.
Your experience with Spark, I never use it. So
yeah. Well, for Spark itself, it's not very difficult to use. I'm not really using any of its advanced functionalities, but actually the way that Spark works on R is that it gives you a method for lapply. And every iteration of the lapply just gets sent to a different worker. So then it's pretty simple. As long as you write a function that uses an lapply and you get something back, then you can just run it through Spark and then it gets done automatically. You just need to also say like how much memory do you need to use, because if you exceed, then it gets killed and things like that. But, yeah. Generally quite straightforward. And then the whole cluster, it's nice. We get quite a lot of cores, but even that is not really sufficient for the big data analysis. And also our cluster then doesn't really have the data. It has neither Landsat nor Sentinel-2 data. So then we're going to transition to DSs that have Sentinel-2 data. But Landsat is still a bit of an issue, and we will need to figure out how to get that data also. So perhaps it's going to be through Google Cloud Platform or something like that, or maybe Google Retention. Yeah, could be also Amazon, who are also looking at that. Okay, and then lastly, since I wanted to mention OpenGeo, so this is what I have about it here. It's a very small slide, but if you have any more questions, I'm happy to answer them afterwards as well. So one way that we could use to solve this issue of big data processing is the other project that I'm involved with, which is OpenGeo. And there's a framework for handling such large amounts of Earth observation data by making use of cloud platforms that are already at the endpoint where the data is located. So we have a lot of disparate cloud platforms. For example, the Terrascope platform itself is built specifically for Proof-of-V data. So they provide the Proof-of-V data. They also provide computing power that can directly operate on the data. And we have also others like DSs that have the Sentinel data. They also provide the processing directly next to the data. But they are different platforms, so they would need to use different interfaces. So you cannot just run the same script on both and expect it to work, because maybe ours is using Spark and theirs uses Slurm or something else. So OpenGeo helps with that, because in there you have a unified API, which is a JSON-based kind of process graph implementation, where you can write what you want to do in R, Python, JavaScript, or if you want, you can make some other clients. Then this process graph gets translated into a JSON object that gets sent to the backend, and then the backend knows how to process the data in the way that you want. And then it doesn't matter what backend it is, it will do the same operations, because the commands that you're asking for are the same. So you can, for example, calculate in DVI. So you say that you have these sequence of commands, this arithmetic operations in the sequence, and then it doesn't matter which backend you're running it on, they will all understand that this is what you're supposed to do. And then the backend accesses the data locally on their side, runs the script that is generated from the process graph, and then it returns the results directly to the user. So you only download what you need in the end. And indeed, this also allows us to run UDFs, which is a very important part. So if we have something like BFAST, which is really complicated, and it's not something that you can implement with just band arithmetics or something else, then you just package your R script itself, you send it to the backend, then you say, please run this R script as part of this processing chain. And then eventually when it gets to that point, it will send the result to the user-defined function. The function itself runs in it in a, usually a container or something like that. And then the output gets put back into OpenGeo, and then it gets pushed back to the client afterwards. So then you can get the best of both worlds, because that way usually the processing of the UDF happens also next to your data and not at your own computer. Okay, so that's about all from that. And just wanted to mention at the very end of the presentation some other things that I work on. So one thing that I'm involved with is the geoscripting course, where you can also learn more about the basics of doing geocomputation and processing spatial data using both R and Python. And the entire course is online, so you can follow it. It includes tutorials about raster vector analysis in both Python and R, and also a bit about Bash and Google Earth Engine. And yeah, I will be more involved with the course as well, because now I'll be lecturing for the Master of Geo-information Science in our group. And I'm also involved with the BFAST package maintenance a bit, because yeah, I use it quite a lot, so I find some bugs every now and again, or some things that could be improved. And now we're trying to get a new version of that running, also because Mars's Apple version, it is there on GitHub, but it has never been pushed to CRAN. And we would like to have that, because it would be nice if people had the ability to also use these improvements in speed, but it also requires to run C++, which is much higher requirements that we have currently. So we need to split it off to an additional optional package that the original package interfaces with. So there's a lot of things that still need to be done. But afterwards, hopefully we'll have something that is user-friendly and easy for people to download. And then finally, I'm also involved with another project, Sensico, which is a project that has several parts. And one of them is directly related to time series analysis. So there, people can learn from one another, from the community of those who are working on time series analysis, and to exchange ideas about what's the best way of doing these sort of things. And also about this field of fluorescence, which is a newly emerging field. And it's based on hyperspectral measurements that can be done both from ground and also from drones and airplanes. And eventually in 2022, there's also going to be a satellite, Flex, built specifically for this task, that we will also be able to see the fluorescence measurements from space, which should allow us to do better accounting of the productivity of photosynthesis over really large areas, which we couldn't do before. And that's something I'm also involved with a bit. All right, so that was the general overview of this. And if you have more questions for this part, then let me know. And then afterwards, we will go into the practical part. The practical part you can find here at the very bottom, and also find this link in the calendar. Yes?
If I understood correctly, you basically used break detections for these time series, which is very what you said, and you able to other aggressive.
Yes. So the question was whether it would be a good idea to use an autoregressive approach instead of a BFAST-like algorithm. There's certainly a lot of other algorithms that can also do something like that. I tested something like super simple by just taking the mean of each year for the vegetation index and then doing a t-test and then seeing whether that is any different from between different years. And that's also a simple method that is definitely much faster than what BFAST can do, but it's also not as accurate. So it's always a bit of a trade-off. Yeah, and in the autoregressive part, it's a bit complicated because it has the parameters for it, and it's not something that you can automatically determine. There are ways to do that, but it's difficult to tell whether it's really valid or not. And BFAST was developed specifically for this detection of breaks in the time series, so then it's fairly easy to understand what it's doing and also to evaluate whether those are real breaks or not. Yes? Yes. Yes, exactly. So we do the updating of the global land cover map by running BFAST on all of the pixels. So these pixels, though, are MODIS pixels and they're not the ProV pixels. Actually, we resampled the MODIS data to ProV 300 meter grid. So it's running at 300 meters. And then based on that, it's applied to all the subpixels at 100 meters. So at least there's a bit less data to run on, but indeed it's a slow algorithm and there's really a lot of data that it needs to handle. So it does take like several weeks to run over these large areas, but the way that it is implemented on Spark, we still have enough cores that it is not a really big issue. So yeah, and also it helps that it detects all the breaks in the time series immediately. So we don't need to run it for every year, but we already get everything in one go. And then another thing is that BFAST monitor for the near real-time detection, it is actually also one order of magnitude faster than BFAST1 itself is as well. And that also helps.
Where to implement some feature parts.
Yeah.
To add some speed.
Yeah, exactly.
Would you have had covariates that are temporal as well? Or is that
Also, these are effectively the temporal covariates, right? So we extract from the time series, the seasonality, and the trend component, and so on. And in fact, indeed, the BFAST-ON can make use of external regressors. So even if you have, say, additional covariates, like maybe climate and things like that, you can also include that into the model as long as the time steps match. So you need to make sure that you don't introduce too many NA values, because if any of the covariates are NA, then all the rest of the variables are also going to become NA. But generally,
you can use the time series aggregator.
Yeah. Yeah, exactly. So then it's the seasonality and the ancillary data will be used in the modeling of the data that we have in the response.
This is just characteristic of BFAST-ON, or it was also before?
It is implemented specifically in anything that is using BFAST PP. So you can see it here. BFAST by itself, I don't think it exposes this functionality. BFAST-ON definitely does, and BFAST monitor also does. So anything that you use BFAST PP on is something that makes use of this. And that stands for BFAST preprocessor. So it takes your inputs and then it decomposes that into the different components, as well as allows you to use these regressors and so on. Yeah. Yes.
does it work for, so in Netherlands and soil science, there's not a lot of monitoring. So I think at max there's maybe like three applications. That's not too little for it to use.
3 repetitions of what?
So it's like three. So instead of having I don't know how many seasons or years you have, you just have like 3 repetitions.
So you mean so like 3 observations?
Yeah, 3 observations at the same location.
Oh yeah, so for the entire time. Yeah, then indeed that would not really work, because yeah, you have to have enough observations in the time series for BFAST to be able to segment it into segments. If you don't have that, then it's completely impossible, because you would need to put a segment on one or a segment on another. And you also cannot have segment boundaries in areas where you have NAs, because it's not clear where the beginning or the end of the segment would be. So only in the areas that are on the left side or the right side of the NA area can be used as the boundary. Right, in that case, we can go to the practical. So it's also shown here. So the practical here is also online, and this is in our Markdown document. If you would like to have the actual R Markdown document, it is on GitHub. So just this URL is the same as the IO URL, just in a different format. So it's github.com/this/bfast4AO, and it's index.rmd. So you can also try to run it yourself if you'd like. I will just go through it in the HTML. And if there's something that you would like to see tested, then I also have the script here running locally on our board. Okay, is everyone there already? And the link you can also find in the calendar. I should probably also put it into. Yes. This tutorial is about how to use BFAST Monitor for detecting breaks in the time series. And it's quite hands-on. It's using Modus, and it is using several packages. These are the packages that you will need, and this function automatically downloads and installs them. One thing that I would like to also do, because this is based on BFAST Monitor, but it can also be based on BFASTON. But BFASTON is only available in the development version of the BFAST package. So I would suggest that you do this first. So install the remotes package, and then do remotes install GitHub bfast2/bfast. And that will give you the development version of BFAST, which has the BFASTON function. Otherwise, when you try to run it, you will run into the error that it does not exist. And if you install it later over the CRAN version, then you will need to restart R, and then all of your objects will be gone, and then you will need to rerun everything over again. In this case, I was trying to see if it's possible to unload the previous version, but it didn't really work. Maybe if I do that before. Yeah, it can take a bit of time to install the packages. If you find that it's a bit too slow, you can omit the leaflet package, because that one is only used for a nice visualization. But the others you need: struct change, bfast2, raster, and noise tools. So the general idea of this is that we will use Modus imagery from the Modus package, Modus tools package. It can download the data from the Modus archive in particular areas. These are related to flux towers. Over those, we have information about things including land cover, and also just the general Modus surface reflectance, and as well as MDVI. So we will be downloading over a particular test site some Modus data. And then we will apply a cloud mask. And then we will apply BFAST monitor, first on a particular pixel, and then later on the entire area, and then we will see what the result looks like. And then afterwards, we will look at BFAST OM doing the same thing and seeing what is the result in that case. So I can just go shortly from top to bottom. So from the very beginning, to look through this, we have this MODIS subsetting website. And this is where we will be getting the data from. We're working with mod 13Q1, global 16-day imagery at 250 meter resolution. There's several bands. And then we can calculate vegetation indices from these bands. And in this case, I believe we are using NDVI. Yes, we are using MODIS NDVI. And so first things first, we need to select a particular site. Since we're in Wageningen, we can select the site that is closest to ours, but it's not necessary. You can also just choose whichever site you like, as long as there's data of NDVI from it. The subsetting website uses this pixel numbering scheme. If you go on it, it's just if I just show it to you. Yes, subset data and visualizations. And we want this mod 13Q1. Yes, so these are the vegetation indices and DVI and EDI. Yes, so we have the time series here. And this is the spatial representation. So when you download a subset, then it will download information about the area that is immediately around this flux tower. So this is the grid that it downloads from. And then there's this pixel numbering scheme because each of these pixels has a particular index. Right, you can also here see the land cover map around the site. And this one is not using our land cover map, it's using the MODIS land cover map, which is at a coarser resolution and generally not as accurate, but it's good as a visualization point. So if you have the packages installed, then you can start downloading the data using this code. So who is still installing packages? And who has the packages finished already? Okay, good. So then we can go forward. So we have this time series function, which is not that important what it does, but generally it just converts the input from the way that it is presented in the subsetting website into a time series that is easy to read in R. Specifically, it is a TS object. And it's done first by making use of zoo and then extracting the time from the time array in a way that it is parsable. And then it aggregates the data into decimal year timestamps so that we have a regular time series rather than just the MODIS observations. And then it's converted back into a TS object, and then that's what's returned because the BFAST package generally works with TS objects. We're trying to implement also using the zoo objects for irregular time series, but that will still take some working. And then this is where you download the data. So you select which product you want, you select what is the site ID. So if you wanted a different site ID than this one, then you can enter a different one. Then which band you want, in this case it's in BVI. You can also try, for example, with EVI. And then from where you want to start, you can also specify the end, but otherwise we'll just download until now. In this case, it's using the entire Modus archive. And then, yeah, the specific site name from the site ID. And then these are just some things, whether you should show the progress and whether the download should be internal. Hopefully it will work for you to download it. Sometimes LPDAC is down for maintenance surprisingly often, and then you need to download the file manual. But yeah. Did you get it to succeed already? Okay, great. And then we have in the Modus tools package also this very handy function. It's been added only recently, T2raster. So it will convert the downloaded data, which is actually just a big CSV, into an actual raster. And then we can use all the raster commands on it. And then the first thing that we want to do is to mask out the clouds. So that's why we have both of these. So we have the vegetation next raster and we have the quality raster. And then we just mask out everything where the reliability flag is set to less than 0 or more than 1. So effectively, we are keeping only the 0 and 1. Everything else is set to NA. So we use the mask function in raster to mask it out. And then we plot the image, and this is what you should see. If you select a different site, you will see slightly different, but probably will look similar with how it's masked out. And oh yeah, this actually shows that we have pixels that have reliability 1 and 0. We don't actually have any other ones. So in this case, we don't get to filter anything out. But in other cases, you might get that. And then if you use the click function, that's quite handy, you can check what are the values at particular pixels. So after you have something plotted, then you can use the click function, click on the particular area, and then it will give you the entire time series, as well as the X and Y coordinates. And cell number, if you also have that. True. And if you want to see a fancy map, then you can also run this part with leaflets, and then it will show you the raster itself that you downloaded and masked. But this is optional, so it's not absolutely necessary. The important part is here, and that's the BFAST monitor. So BFAST monitor itself only knows anything about time series, and it doesn't know anything about rasters. So we will just be using the raster package to apply the same algorithm on every pixel in our raster. So first of all, we just try on a single pixel. We just select one pixel, the pixel 78. It could be anything different, just out of the number of pixels that we have. And we use the function timesare to convert the input raster values into this TS object. So it needs to have the pixel time series itself as a vector. By default, if you do just like this on a raster, you get a matrix of one column, which is weird. Okay, so you can just convert that into a vector again. And then you also have the dates and the names of your layer. So we just need to parse that, and as date will parse it. Starts with an X and then the year dot month dot day. And then that just gets put into this TS object. Then if you plot it, you should be able to see it. And then after we have the time series, we will try to detect the breaks in this time series. So we can directly run BFAST monitor, which is a function. The first argument is the time series, and then the formula. So what kind of output from BFAST BP do you want to use to predict what should be in the future? So here we're using trend and harmonics with order 3. And then an important thing is to say what is the starting time of the monitoring. In this case, we put the starting time as the beginning of 2019. Yes. So the harmonics is what you see here, the harmon cos and harmon sine. So the way that it works is that we're trying to fit sine and cosine waves on top of our seasonality. And then that can have a different frequency and different interval. And that's the harmonic order. So if we have order 1, then we would only have these cos 1 and psi 1. So these ones, this one and that one. So they can capture the seasonality that happens during the entire year. So there's one peak during the year and everything else is lower. If we have a harmonic order of 2, then we can capture 2 things per year. So perhaps there's a double season, maybe there's some crops going on somewhere, so then we can capture that seasonality as well. And then the third order can capture even more seasonality, even the local changes during the different parts of the year, and so on. But the more orders you have, the better we can model the data, but that means that we are risking overfitting. And if we're overfitting, that means that we will get a lot more breaks than we should, because it will find that any deviations from this normal overfitted part is considered to be a break. And then there's also the seasonal dummies. So here they're shown as numbers, but they're actually not numbers, they're categorical variables. And the seasonal dummies tell you which season it is. So if you have 4 seasonal dummies, for example, then you can interpret that as whether it is summer, spring, autumn, or winter. So for each part of your time series, you will have just a label indicating the season that it has. So if you want to use the seasonal dummies, then instead of using harmon, you would use plus season. There was a bug in the mainline version of BFAST. Actually, yeah, the bug was actually in Maris Apple code because he optimized it a bit, and the seasonal dummies were always interpreted as numbers and not as factors, and that messed it up a bit. I fixed this issue now, and then with the latest development version, you can use the seasonal dummies, and you can also, which is a new thing that I implemented into the development version of BFAST, you can set how many dummies you want. So it's a parameter called sbins. So for example, if you set sbins equals 4, then you will have the 4 seasons. If you set it to more, you will have more seasonality, so it can model even smaller changes during the seasons. Yes, so when we run this, we should get something like this. And then you might be wondering how to interpret this. So we have the black part, which is our original data. Then we have the area that is, well, first we actually have this red line that is the time of, the black line, the black dashed line, that's the start of the monitoring period. So this is what we defined as from which part do we want to start monitoring so that we would know after this part whether there has been any break or not. So that's just something that we defined in the function itself. Then we have, so the way that the algorithm works is it tries to detect what was the stable history. So from this line, it goes backwards, and it tries to detect breaks first that would be behind it. And here it determined that the stable history goes to, yeah, sometime in 2012 or so. So it will take this stable history as the basis of what it expects to also see in the future. And it actually just ignores this whole part altogether. So you can only look at this part. Then based on that part, it will do the BFAST-BP thing. So it will determine what is the seasonality, what is the trend, the harmonics, and so on. And then this is plotted as the historical data model in blue. And then after it has this model here until the start of the monitoring period, it will extrapolate this model to the future. And then the way it works is it tries to see whether the real data in the future after this point is sufficiently similar to what it was before. So obviously it also knows how much of a deviation the points had in the past. So if we have similar deviations in the future, that's also fine. That means that nothing has really changed. But if we have deviations that are different, then you can have a break. And in this case, it did detect a break because compared to our predictions, we have a lot of values that are much lower, and they're much lower than also in the history period. And the detected break here is actually the first instance at which there was enough evidence that there is a break. So it's also using the cumulative sum of deviations. So after some time, it will determine that there was a break or not, but that does not mean that that's the biggest break or that's the most prominent break in the time series. It's just the first time that the threshold has been exceeded and we know that there is a break. At the top, it also says when the break has been detected, but again, the timing is not exactly precise, just to get an idea that there was a break detected here. Yes, and then what if we want to do this for all pixels? Well, we need to make use of some raster functionality. So first, we get the dates. Well, obviously, any dates are the same for all the pixels, so we just get a vector of dates. And then we define a function that we want to run on every pixel. So it's using the same thing. We have BFAST monitor in there. We have the same parameters. We need to also do the time share part so that we get the input TS object. And then we also need to return something that is only numbers, because actually the BFAST monitor function returns a complex object that includes all kinds of interesting things. But that's not something that you can easily put into a raster because that only can handle values. In this case, it's returning the breakpoint timing and the breakpoint magnitude. And then afterwards, we use the calc function and say on our vegetation index, run BFM raster. And then afterwards, just to make it a bit nicer, we give it nice names, and then we plot the result. Then you should get something like this. So how to interpret this is that here we have the timing of the break, and it shows at which point in time the threshold for whether there's a break or not has been exceeded. So the earlier it is, then the quicker the threshold has become exceeded. And the magnitude of change will tell you how different it is. So how much deviation there was from the modeled seasonality and trend compared to the real seasonality and trend that was observed. So in some cases, you might see that there's bigger or fewer ones. And even places that generally don't have a break detected, you see that those are NA values. They still have a magnitude of change because we still detect that there was some sort of change between the model data and the real data. So it's an indication of how stable that pixel is. Yes. And then we can just run it for different pixels. If you use the click function on your original vegetation index, you get the time series, and then you can get the time series from these particular locations as well. So you can get a bit of a better idea of why the algorithm decided that there is or is not a break. If we want to get all the information, just like we had here, then we still need to rerun it for a particular pixel, because otherwise this data is just not saved into the raster. Yeah, so that's about it from this side. So most of the way there. Are there any questions at this point?
Block in 2020.
Yeah.
If you see the plot just a node, so it's just the time series.
Yes.
Is the red line indicated the upper peak, or is it below? What is it? I mean, the break is because it's the red.
Yes, so the line of the break is the red dashed line. And in this case, it is pointing towards not the peak, but it is pointing towards one of the points that are lower. But indeed, as I mentioned, this is not necessarily very precise because it's just telling what is the first point at which the threshold for whether it's a break or not has been exceeded. So frankly, the peaks themselves, they added a lot to this cumulative sum, but not enough to consider the break by itself. And then the point afterwards was when it tipped over and then decides that there was a break.
So I can say that my red line identify a location where left-hand side has different track. This is what I can say.
Yes, so that means that the location of the red line shows at which point there was already enough evidence that there was a break. So indeed, there was enough change before the red line to consider this to be a break. Yeah. Yes?
And I also expect to look into the sample for information that I don't have happens. You know, the real
Oh, so if you, so you mean that whether you can get the model parameters for the predicted model also in the past, or the, well, yeah, in the future because it's the same model. Yeah. Yes. So you can reconstruct this model that is shown in blue by looking at the BFAST monitor object. And in the object, it includes the coefficients. So the coefficients are related to the BFAST BP. So you know what to multiply your inputs by so that you could reconstruct this entire model. And then using the same coefficients, you can extrapolate it in any sense that you like. So that. I'm not sure if for BFAST ON is implemented, but at least for BFAST monitor, but for BFAST ON, there is simply a function called coefficients, and it just returns you the coefficients of each of the parameters that we had, so each of the parts of the BFAST BP. Then there was also a question in Zoom. If we set the break to another time, will the output be different? And if yes, how do we explain it? Yes, the output will be different for two reasons. If, say, we set the time to a previous time for monitoring, then the stable history will be calculated back from this previous time, and it might be different. So for example, if we said here, then the stable history will no longer be this area, but rather the stable history will be this area because it was increasing at the time. And then it will try to see whether there have been any breaks since here, if we extrapolate this model from here. And then it will definitely see that, yes, there was a break, and there was a break over here already, because this was going up and now it's going down. And then you will definitely get a different result. It's also a correct result because, yeah, we can see that there was a break. Sometimes it might also give spurious breaks, and that's also where parameterization kicks in, and that's one of the things that I was doing to try and figure out what would be the best parameterization for a generic global land cover detection. And generally what I found from that is that simpler parameters are better. In fact, the best one for BFAST monitor that I could find is only using the trend and actually disabling this automatic detection of history. As you can see, it stops actually quite early. And if we just disable and say use the entire history, it will learn from the entire time series. And usually there's not so many breaks that it would be bad for estimation of the time series.
So you suggest do not take the full time series?
No, so what the best was to take the time series, the entire time series, and not rely on this automatic detection of when there is a stable history. To just take the whole thing and consider the whole thing to be stable. Then if we have a trend only throughout the entire time series, then we can check that if there was really a big decrease or really big increase, then you can detect that change. And if there was just some random noise, then it will not detect that there was a change. Because if you look, for example, even in this case, there isn't really that big of a reason to detect a change here, actually, because there were in the history some big spikes like this as well. And probably here there would be a break, but that's maybe one of the only breaks that you can find in time series. Yes. And then for the next part, we can do the same thing, but using BFASTON, and it's also just as straightforward. So as long as you have the development version of the BFAST package installed, you will have the BFASTON function. And then it works pretty much the same way as BFAST monitor. You just get the time series as a TS object. You give the formula, same formula for BFAST BP, and same order parameters. And then in the end, it gives you information and it says whether it found any breakpoints or not. And in this case, it didn't find any breakpoints. And this was actually from the previous example, so this one. So it says that, yeah, according to BAC, there's actually no breakpoint throughout the entire time series. If we try some other pixels, you might find one that actually does show that there was some change. So in this case, if we use the pixel 92, it says that there was a breakpoint. You can also see at the top here it says optimal one-segment partition. So what this means is that the optimal way to partition the time series is a single segment, which indicates no break. In this case, it says it's optimal two-segment partition. That means that the optimal way to partition your time series is into two segments. And obviously there is a break in between those two segments, so there is one break. And then it also returns all the breaks that it has detected. In this case, one break, an observation number 327, and it is at 0.8 of the entire time series. At the moment, it's not as user-friendly as it could be because it doesn't actually tell you the dates at which it was detected. So you need to figure it out by yourself because it depends on the input. So we need to do some time manipulation because if we just take this observation number 327 and we try to say that it's the date number 327, that would be wrong because we might have NA values, and those NA values are removed, and this number corresponds to the time series with NA values already removed. So then we need to remove those values from our original dates, which we do with NA omits, and then that is correctly corresponding to it. Then we see that the break that was detected was in 2016. And then we can plot that manually as well. We plot the original time series and we add a line indicating where the change was. And here it shows that there was an increase. And at this point, it stopped increasing and it went straight. This is a very basic plot because for BFAST-ON, we don't yet have a function that would plot it, especially because of this issue that we don't have the dates directly from the object. And I will try to implement this plotting sometime in the future because as long as we can cache these dates, then we can do the plotting as well. For now, it's not yet implemented. So in this case, BFAST-ON will be able to detect all the breaks in the time series. If there's more than one, it will also detect that one. So you can also try to, for example, create a raster, just like we had with BFAST Monitor, to see spatially where there are breaks. But with BFAST-ON, it's a bit more complicated because it can detect more than one break. So if you try to do that and you have two breaks, for example, then raster will fail because it will say, oh, there's 3 layers and you were doing 2 layers before. What's going on? In that case, you can just try to take, for example, the first break or the last break time series, and then you can get an output. Like I said, in my case, when I did this for the project, I just made a yearly layer. And then since my age was set to 1 year, that means that I could not possibly have more than 1 break in a year, which means that there was no problem with that. So for every year, I would just say whether there was a break or there wasn't a break. In this case, you can just do something simpler if you want to try that. Yeah, so that's about it. So now you can just try to play around with this, try different parameters, different areas, and see what it does and how it works. At the end of this tutorial, there's also a bit of information about this seasonality monitoring using harmonics. So exactly how to derive those sines and cosines. So this is basically what the BFAST-BP function does for you. So you don't have to do that yourself. That can be quite interesting to look at. And this is an overview of the new things in the development version of BFAST. So I implemented this LWZ selection. This is actually not in BFAST, but it's in struct change. And the struct change package is what provides the core for the BFAST package. So for being able to use a lot of these, you actually have to also install the development version of struct change. So it's also BFAST2/struct change. Yeah, and then you can use LWZ to select the breaks instead of the default BAC. And you can also plot the result from the breakpoints function that shows you all the different statistics, including LWZ and BAC. So basically, this plot at the bottom. And you get also an indication of R squared. So how well does your model fit your data? And you also get the break magnitudes in different ways. And finally, this SBINS parameter, which allows you to customize the number of season bins. Okay, I have a question from Zoom, whether there is sample code of the new things about BFASTON. It's still currently under development, so I will definitely try to make some tutorials or so. For the new things that I added, so the BFASTON function itself, for example, we have the help function, and in the help function you can have examples, and there I also added an example of how to run BFASTON. But there isn't really like a blog post or anything yet for how to do these things. It is a good idea to write it down, but I don't yet have the time to actually do so. It's something that is already, I think, an issue on the GitHub. I can show this as well. So we have bfast2/bfast, and that's the GitHub repository for the development version of BFAST. And if you find any issues, then feel free to open a new issue, and then we will look into that, including if something is wrong with the output or anything like that. If you get some weird errors, if you're trying to do something. And we have some documentation things to add, like to add install instructions or to write a tutorial about how to use these new additions. So hopefully we will have that by the time that we can update it on CRAN, but so far it's under development. I hope Zoom can still hear the audio.
So I have a quick question about the 10 segments.
Mm-hmm.
This example, we have 2 segments.
Mm-hmm.
So this is decided by the criteria.
Mm-hmm.
So the criteria then can be arbitrary number.
Yes. Indeed. So for example, if you set the criterion in the new version, the development version of struct change, I can also show this that we have BFAST2/struct change. And also Marius Apple is helping to maintain the struct change development version package as well. We have the ability to also use breaks equals, and then you set it to, for example, LWZ, or you set it to RSS, and then it will optimize it for this criterion. So if you set RSS, then usually it detects an incredibly high number of breaks, almost as many as it can. And if you use LWZ, it will detect much fewer breaks. And also, already in the current version of struct change, you can set breaks equals and then an arbitrary number. And then it will just tell you how the breaks would be allocated if there were indeed 2 breaks or 3 breaks or so on, depending on the number that you pass. Just breaks equals and then the number. Yes.
Is there an easy way to get small design so now we have for these sites?
Yeah. Now let me check quickly. So it's notice tools, not tools, that would be expensive. And it's the MT. Oh yeah, the question was whether you can use modus tools to get the information about an arbitrary location. So here we have empty subsets. So let's just check. I'm guessing that at least this function doesn't allow you to do that. Product band. Oh, it does have that long actually. And this is in kilometer sample from left to right. So I assume that you would be able to get it for that, yeah, because site ID just overrides the lat long, so you don't need to specify it. But if you want, you can specify just your lat, and then it should give you the information. Yes. Of what? Which one do you mean? Which one do you mean? Because, yeah, most of the words should be there. Do you mean this one or? Yeah, so yes, I can. That was on to parse itself, so. We also have some nice vignettes. Yes, it does have it. So I just, yeah. Yeah, I can send it to later, yes, because I don't have Metronomes running at the moment. I can send it into the chat of Zoom. It's a good point that if you want to find any of the links that I mentioned and you don't immediately see them, just feel free to ask me on Metronomes and I will just post them there. Yes.
So how far away, how far back?
Yeah. Yeah, so the question was, yeah, how does the model determine what is the stable history period? So the history period is actually determined, well, maybe I can also show it here. There are some options for that. So here you have history, and it says ROC, BP, and all. So I mentioned this history equals all. That means don't even try to detect what is a stable history and just consider all the history to be stable. BP actually means run BFASTON and then determine what is the stable history based on BFASTON. And ROC means to do reversed order cumulative sum. So it's just reversing the time series and trying to do the change detection the same way that it's doing with in BFAST monitor. And if it detects that there's a break, the same way that there's the cumulative sum that is exceeded a particular value, then it will say that that's a break, and then that's the end of the stable history period, and then reverses it back again. And also you can have some different parameters for that. So for ROC, there is this level option. And actually this level specifically here corresponds to both the level for the history determination. So that's the P value at which it determines that there's a break or not. And for example, if you want to have fewer breaks detected, then you can set the level to be smaller, like 0.005. And it will also will affect the history. That means that it will be more lenient as to what is considered to be a stable history. In the CRAN version of BFAST, this is just one number. In the development version of BFAST, this has become a vector of numbers where you can specify the p-value level both for the detection of the break in the monitoring period and in the stable history separately.